For the first order initial value problem, the differential equation has the first derivative and has one initial condition. For the second order differential equation, you need two initial conditions. The first example, we have to find three things. For examples, number one, find the general solution to the differential equation. Sketch the family of solutions. Find the particular solution using the initial condition and trace the curve that best represents the particular solution. In part A, we have y prime equals 2x plus 3. And this is the first order. For the first order, we need one initial condition. Part 1, find the general solution. So y equals the integral 2x plus 3 with respect to x. That gives us x squared plus 3x plus c, which is called a general solution, or the one parameter solution. Part 2, sketch the family of solution. For c equals 0, the solution will be y equals x squared plus 3x, which is a parabola, the intersection point at 0 and negative 3. For c equals 2, y equals x squared plus 3x plus 2. If you factor quickly, we have x, 2 here, 1 here, or tells us about the parabola having the intercept at negative 1 and negative 2. Repeat the same manner. It's more convenient to use the tool to graph for us. So this one, as you see on the diagram, so you have the family of the solution or the family of the parabola graphs at different values of c. And for part 3, find a particular solution. The initial condition, y at 1 equals 2. We are going to find c. So 2 equals 1 squared plus 3 times 1 plus c. Or c equals negative 2. Therefore, the particular solution is y equals x squared plus 3x minus 2. As you see, the solid curve occur when c equals negative 2. And the initial condition at the point 1, 2. The point 1, 2 is located on the curve where c equals negative 2, or the particular solution that is passing through the initial condition point 1, 2. Next example, fill the first order differential equation. Y prime equals x times e to the power negative x. Part 1, find the general solution. Y equals the integral x e to the negative x with respect to x. This one by part technique is required. If you recall, integral of the v du equals u times v minus for this example, y prime equals x times e to the power negative x with the initial condition y at 0 equals 0. To find the general solution, y equals the integral of x e to the negative x with respect to x. This integral requires by parts technique. If you recall, its integral u dv equals u times v minus integral v du. The Lie technique is very helpful to determine which one is u, which one is dv. And we know x as the algebraic function. E to the negative x is the exponential. So u is x, dv is e to the negative x dx. Therefore, dx is du. V is negative e to the negative x. So y equals u times v, or negative x e to the negative x minus the integral v du. V is negative e to the negative x, du is dx. Simplify a little bit. And then one more time of the antiderivative. So we get negative e to the negative x for the second term, and then plus c as the general solution. Part 2. For different values of c. For c equals 0, for example, y is negative x e to the negative x minus e to the negative x. For c equals 1, y is negative x e to the negative x minus e to the negative x plus 1, and so forth. And as you see the graph on the side, for different values of c. Part 3. Find the particular solution using the initial condition. Y at 0 equals 0. So 0 equals negative 0 e to the 0 minus e to the 0 plus c, or c equals 1. Therefore, the particular solution is y equals negative x e to the negative x minus e to the negative x plus 1.